Picture a thread thinner than a human hair, so thin you can barely see it, and yet, weight for weight, stronger than steel. Not in a fairy tale, not in science fiction, but in an ordinary forest strung between two branches. Something the size of your fingernail spins it every day. This thread is a spider's web, and it's stronger than it has any right to be. That same web you brush off your face in the woods is one of the most extraordinary materials on the planet. From it, the spider weaves a trap that catches beetles and flies in mid-flight, absorbs the impact, and doesn't break. Light, thin, nearly invisible, and incredibly strong. We're used to not noticing it, which is a shame, because inside it is a genuine marvel of engineering. This seemingly fragile little thread is capable of remarkable things. If you could braid spider silk into a rope as thick as a pencil, it would support an enormous load. Spiderweb rivals steel and Kevlar, the very material used in body armor, for strength. And all of this comes from a weightless thread spun from a spider's abdomen. How is that even possible? And here's the unexpected turn. We've borrowed the secret of spider silk's strength from the spider itself. And now, we're learning to make from it eco-friendly clothing with no petrochemicals and no microplastics and medical sutures that the body quietly dissolves on its own over time, without a single spider involved. This is the story of how a hunting web in the forest became the fabric of the future. First, what's the puzzle? We know how to make strong materials, steel, titanium, but they're heavy, and smelting them demands enormous temperatures and energy. A spider, on the other hand, spins a material that rivals steel for strength right inside its own body, at room temperature, out of ordinary protein. No furnaces, no chemicals, no toxins, and that seems almost impossible. To truly appreciate how remarkable spider silk is, we need one concept: specific strength. That's strength adjusted for weight. Simply comparing materials by who holds more load isn't fair. A steel cable will obviously outperform a thin web in raw pull. The fair comparison is at equal weight. And that's where spider silk does something remarkable. Gram for gram, it holds just as well as steel, and sometimes better. And that's the holy grail of material science, being both light and strong simultaneously. Usually, you have to choose one or the other. Either it's tough but heavy, like steel, or light but fragile. Spider silk somehow manages to be both. Per unit of weight, it's one of the strongest materials on the entire planet. Engineers can only dream of something like this. But if strength were the only story, spider silk wouldn't be all that special. Glass, for instance, is strong too, but it's brittle. Hit it hard enough, and it shatters. Spider silk is also extraordinarily tough. And it's that combination of strength with toughness that makes it truly unique. To understand what makes this possible, let's unpack what toughness actually means. Toughness is a material's ability to absorb the energy of an impact without breaking. Not just bearing a large, steady load, but surviving a sudden jerk, stretching without snapping. Glass can't do this, it's strong but brittle. Spider silk, by contrast, can stretch significantly, absorb the blow of a flying insect, and not tear. It's both strong and extensible at once. Think about what a catching web actually needs to do. A beetle flies into it at full speed. If the web is simply stiff, it'll snap from the impact or the beetle will bounce off. If it's simply soft and stretchy, the beetle will push straight through and escape. The web needs to both spring back and absorb the blow, while also holding the prey without tearing. Combining the incompatible. And nature solved this at the molecular level. The whole secret lies in the silk's molecular architecture. A spider's thread only looks uniform. Inside it, there are two completely different components working together as a pair. One provides strength, the other provides extensibility. And it's their partnership that produces the magical combination of properties. Let's go through each of them. The first component is rigid crystalline regions, which scientists call beta sheet. These are regions where protein molecules are arranged strictly, densely, and in perfect order, like bricks in an ideal wall. These tiny crystals are very strong and hard. They're the structural reinforcement of the silk, its load-bearing skeleton. They carry the main tension, but on their own, they'd be brittle. Which is why there's a second component, a soft, amorphous matrix. Amorphous means without clear order. Here, the protein molecules are folded and tangled, like coiled springs or a loose ball of yarn. This region is flexible and extensible. It fills the space between the rigid crystals and binds them together. If the crystals are the rebar, the matrix is the elastic rubber encasing it. And the partnership between them does something remarkable. Picture hard bricks embedded in soft, stretchy rubber. The bricks are the crystalline beta sheets, the rubber is the amorphous matrix. When you pull the thread, the hard crystals resist the tension and prevent it from stretching too easily. Meanwhile, the soft matrix between them stretches, springs back, and absorbs energy. Strength from the crystals, extensibility from the matrix, in a single thread. And here's what happens on impact. A sudden jerk, say, a fly hits the web. The soft matrix instantly stretches and absorbs most of the impact energy, acting as a shock absorber. The hard crystals, meanwhile, hold the thread together and keep it from tearing. The impact is absorbed, the thread is intact, the prey is caught. Two components backing each other up. Mediocre in isolation, but together something close to a perfect material. That's the whole trick. Usually, a material is either strong and stiff, or soft and extensible, one of the two. Spider silk combines the best of both worlds, the hardness of crystals and the elasticity of the matrix. That's the source of its extraordinary toughness. It doesn't have to choose between strong and stretchy, it's both at once. An architecture built from two different components beats any uniform material. This subtle connection between structure and properties was carefully analyzed by researchers. In 2012, Tokareva and colleagues published a review article on silk in the journal Acta Biomaterialia. They showed exactly how the fiber's construction, crystals plus matrix, gives rise to its properties. They connected structure, function, and the resulting material qualities into one coherent picture. They turned the miracle of a spider's web into engineering knowledge. The central conclusion is simple and profound. A material's properties are born from its structure, not from some special ingredient, protein is protein, but from how that protein is arranged, how many rigid crystals, how much soft matrix, how they're positioned. Adjust that architecture and you can tune the silk, stronger here, more extensible there. And this insight became the key to reproducing silk artificially. You might think, if spider silk is this good, why not farm spiders and harvest it, the way we've been harvesting silk from silkworms for centuries? After all, regular clothing silk has been made exactly that way for ages, raising silkworm caterpillars and unwinding thread from their cocoons. Surely, the same can be done with spiders. Except, with spiders, this approach simply doesn't work. And for a rather entertaining reason, spiders are cannibals. Pack them in together densely, and they'll eat each other until one well-fed winner is left. Silkworms sit peacefully side by the thousands, but a crowded spider farm would quickly become an arena. Farming spiders in bulk for silk is simply not possible. Nature gave us a wonderful material, but flatly refused to hand it over wholesale. And for a long time, that was a dead end. The material engineers dreamed of existed, but you couldn't get it in useful quantities. A single spider yields a tiny amount of silk, and millions of spiders can't coexist. It seemed like spider silk would remain a laboratory curiosity forever, an unreachable dream. Until biotechnology stepped in and offered a workaround, one brilliant in its simplicity. The idea went like this. What if we don't need the spider at all? Silk is just a protein, and protein isn't produced by the spider as such, but by the instructions coded in its genes. What if you took those instructions and handed protein production off to something else, something you can grow in enormous quantities, like tiny microorganisms? And that idea worked. Scientists learned to take the gene responsible for spider silk protein and insert it into microorganisms, bacteria, or yeast, for instance. Now, these tiny workers, following someone else's blueprint, produce silk protein themselves. They're essentially transformed into living microfactories. And they can be multiplied without limit, with no cannibalism in sight, unlike spiders. This process is called fermentation, and it works a lot like brewing beer or baking bread with yeast. In large tanks, microorganisms are fed sugar. They grow, multiply, and in the process produce the desired protein. Only instead of beer or dough coming out the other end, it's spider silk protein. Instead of a web in the forest, a massive vat of protein in a bioreactor. The silk is, in a sense, brewed. That harvested protein is then extracted, purified, and spun into fiber, much like a spider draws silk from its own silk gland. The result is a material that replicates the structure and properties of real spider silk. The same idea of crystals and matrix, just made by human hands. The miracle of nature can finally be reproduced in industrial quantities. This technology has real names behind it. One of them is the Japanese company Spiber. They developed a fermentation process in which genetically modified microorganisms produce silk protein without a single spider involved. They named their material brewed protein, which is exactly what it says on the tin. It's brewed like beer, a protein of the future from a large tank. The American company Bolt Threads took a similar path. They also set up production of proteins that mimic the structure of spider silk through fermentation and named their material microsilk. Different companies, different names, but the same core idea. Reproduce the brilliant architecture of a spider's thread using microorganisms and turn a laboratory marvel into a real fabric you can wear. And this isn't just papers and promises. Real objects have already been made from this brewed silk, including actual pieces of clothing, to demonstrate that the technology works. Biotechnological spider silk has stepped out of the lab and into the real world. Not in every store yet, but the hardest and most important step from a web in the forest to a spider-free factory has already been taken. What comes next is scale. Now, why any of this matters? And here we need to talk about a serious problem with modern clothing. Today, an enormous share of our fabrics is synthetic. Polyester, nylon, acrylic. These are essentially forms of plastic made from oil. Cheap, practical, but that cheapness carries a very unpleasant cost for the planet. One we rarely stop to think about. Yes, a large portion of our clothing is literally made from oil. Polyester and nylon are petrochemicals, relatives of plastic bottles just stretched into fiber. Their production consumes non-renewable resources and large amounts of energy. We wear refined petroleum products and never even notice. And when that clothing wears out, the second part of the problem begins. Synthetic clothing doesn't break down in nature, it's plastic, after all. And with every wash, it sheds the tiniest fragments, microplastics. These minute plastic fibers flow out with wastewater, into rivers, into oceans, into fish, and ultimately into us. Microplastics are now found essentially everywhere, and a significant share of them comes directly from our synthetic clothing. And this is exactly where spider silk offers a completely different path. It's protein, not plastic, which means it's biodegradable. Once it's done its job, it can break down naturally in the environment without leaving an eternal plastic footprint behind. No microplastics, no oil going in. Clothing made from protein-based silk could return to nature at the end of its life, rather than sitting in a landfill for centuries. That's a meaningful difference. And its production is far cleaner too. Remember, a spider spins silk at room temperature without toxic solvents. Biotechnological silk inherits this principle. It's produced by microorganisms under gentle conditions, and the raw material is not oil, but sugar, which can be grown renewably. Less energy, less toxic chemistry. Not only is the material itself environmentally friendly, so is the process of creating it. Put the picture together. Clothing made from spider silk is durable, lightweight, comfortable against the skin, and above all, free from petrochemicals and microplastics. It wears out and calmly biodegrades without poisoning the planet. This is a potential answer to the enormous environmental problem of the textile industry. Not from oil, but from protein. Not in landfill for centuries, but back into nature. Clothing that doesn't wage war on the planet. But textiles are only half the story. Spider silk has a second powerful application: medicine. And here its properties are an almost perfect fit. Silk is strong, biodegradable, and at the same time well tolerated by living tissue. The body accepts it calmly, which means it can be used to make materials that work directly inside the body. Surgical sutures, for one. When a surgeon closes a wound, they use sutures. Often those stitches have to be removed later, a separate, not especially pleasant procedure. But there are sutures the body gradually dissolves and absorbs on its own, and spider silk is an excellent candidate for exactly this. The wound is closed, it heals, and the suture quietly dissolves inside. Nothing left to remove. Why is silk so well suited for this? First, it's strong. It will reliably hold wound edges together while they heal. Second, it's extensible. It won't cut through tissue during movement, but will spring back instead. Third, it's biodegradable. It will safely disappear over time. And fourth, the body accepts it without a strong rejection response. Strength, flexibility, dissolvability, and biocompatibility in a single material, a rare and valuable combination. And medicine doesn't stop at sutures. Biocompatible silk could be used for other things too. Scaffolds on which new tissue is grown, wound dressings, reinforcing meshes. Anywhere a strong, flexible material is needed that can do its job inside the body for a while and then safely dissolve, the same spider principle in service of surgeons and those recovering from injuries. Stop for a moment and take in the scale of this. The same idea crystals of strength in a stretchy matrix works in a spider's catching web, in an eco-friendly t-shirt, and in a suture that dissolves inside the body. From a web in the forest to an operating room. A strong, light, biodegradable material born from a single molecular architecture. A solution nature found that turns out to be needed by us in so many different places. But let's be honest. The spider is an inspiration and a model, not a blueprint to be copied one for one. Reproducing silk that's as perfect as the real thing, cheaply and in enormous volumes, is an enormous challenge. In some properties, genuine spider silk remains an unrivaled benchmark. Nature supplied the principle. Catching up to its craftsmanship in the fine details is a separate and substantial undertaking, and the difficulties are real. Getting microorganisms to produce large quantities of high-quality protein and then spinning that protein into a fiber with exactly the right structure is extremely hard. What matters is not just reproducing the protein itself, but getting the internal architecture right, the crystals and matrix in the correct proportions. Doing this cheaply and at industrial scale is something scientists and engineers are still working toward, step by step. And that's entirely fine. The spider was solving its own problem, weaving the perfect catching web, not clothing humanity or sewing up wounds. Our job is to spot the underlying principle in its silk and adapt it thoughtfully to our own needs. The idea of combining rigid crystals with a soft matrix turned out to be invaluable. The production details get refined by engineers for each specific application, whether fabric or surgical thread. So what did we really take from the spider? Not the literal web itself. We took the molecular idea, joined hard and soft, crystals and matrix, to get a material that's both strong and extensible at once. That idea is now being realized by microorganisms in bioreactors. The principle from a spider's web has made its way into clothing and medicine. A small spider taught us how to make materials smarter. So it turns out, an unassuming spider in the corner is a brilliant materials engineer. It creates a material comparable to steel in strength, without furnaces or oil, at room temperature, from ordinary protein, and has been doing so for millions of years. We're only learning to replicate what it has long mastered, and doing it far more cleanly and sustainably than our own industry. Nature, once again, was ahead and far kinder to the planet. And the spider also changes how we see something ordinary. We're used to thinking of cobwebs as something unpleasant to brush away and forget. But it turns out a web contains the recipe for the material chemists dream of: strong, light, eco-friendly. In the most mundane corner of the forest hides an advanced technology. Sometimes the future of materials is hanging right in front of us, literally on a spider's thread. Put it all together. A spider spins a thread thinner than a hair but strong as steel. And stretchy too, thanks to the partnership between rigid crystals and a soft matrix. We've decoded that architecture and are now learning to brew that silk without spiders, using microorganisms, and to make from it eco-friendly clothing and sutures that dissolve inside the body. Nature's strength without harming the planet. Here's the thought to leave with. Sometimes the most advanced material of the future isn't something invented from scratch in a laboratory, but something nature has been making in the forest for millions of years, and we're only just learning to understand. The answer to the problem of plastic clothing may have been strung between branches above our heads this whole time. All it takes is looking at a web and asking how it's built. And one more thought in closing. We tend to assume that progress means something synthetic, artificial, remote from nature. Spider silk shows the opposite. The most advanced solution can be completely natural and eco-friendly along with it. Maybe the future of materials isn't about squeezing more out of oil, but about learning from living things, like this spider. And spider silk's future stretches even beyond clothing and medicine. Lightweight, strong composites for engineering, protective materials in place of heavy armor, eco-friendly packaging instead of plastic, ropes, nets, and next-generation fibers. Everywhere strong but dirty plastic and heavy metal hold sway today, protein-based silk could one day offer a clean and light alternative. One spider's web and a whole fan of possibilities. A tiny spider that spins a thread stronger than steel gives us the hope of clothing without oil and sutures that dissolve inside the body. It all comes down to the union of hard and soft, not expensive furnaces. If stories like this are your kind of thing, there are plenty more ahead. Next time, how a mussel clings to a rock in crashing surf, and what it taught us about making glue that works even underwater. Until then, keep looking at the world around you and asking, why does that work? Thank you for being with us. If you find the idea inspiring that nature is our greatest teacher, share this story with someone who still enjoys being amazed by the world. We're already preparing the next one, because nature still holds so many secrets waiting to be discovered. See you next time. Subscribe.